Hello, I'm back. This is something that we did not cover. Last time I did the lecture. It is more of a conceptual topic, and we were just looking at the results of all of this, in that we learned how activating groups work and how they direct the and that they direct the incoming substituent to either the ortho or the para position, and then how deactivating groups mostly send the incoming group to the meta position. So we're going to look at it in a little bit more detail right now. And so now we're going to look at it in a little bit more detail. You know the results, but I'm going to look at how this happens and so on. And you'll see what I'm talking about as we go along. So this is section 18.7, and I'm starting from slide 37. So when you have a group like CH3, we call that an activating group. And in this case, the products are mostly ortho and para. Okay. These products predominate, which means that's what you'd have more of, and very little of the meta. So we have 63% of ortho and 34% of para. And we also said there's only one para position as opposed to two ortho positions. So you'll have theoretically 66% of the ortho and 34% of the para. That is, if the group, the activating group, is a small alkyl group. And here I'm not going to go through this because this was already done in detail. So when you draw the product of the reaction where you have the CH3 group present initially and your NO2 group is going to come and attack the ortho position. Okay, so what happens when the nitro group goes to the ortho position? The resonance structures that are drawn, there are three of them, but you see the one that has a positive charge adjacent to the carbon of the activating group. And because this is electron donating, it stabilizes the positive charge. And therefore makes that resonance structure more stable. Of the three, this structure is the most stable. Now, when the nitro group is attached to the para position, you again get three resonance structures, and the positive charges are in the exact same spot as you would have for the ortho attack. And also, this positive charge for this resonance structure is adjacent to the electron donating group or the activating group. And therefore, this is more stable than the other two. And of the three, this is the most stable. Now, when the nitro group attacks the meta position, you do get three resonance structures like for the ortho attack and the para attack. But it so happens that this positive charge is not here. That's because of the location of this third position. This positive charge is not at this carbon. And therefore, you get three structures, but they're all of equivalent, of equal stability, and you do not have one that is better enhanced by resonance. So this is preferred, this is also preferred, and this is avoided. So that's why we say the CH3 group and any activating group like the CH3 group will have more of the ortho product and the para product and very less of the meta product. We also looked at this last week, and we said that for the ortho attack and the para attack, the intermediates, they have an activation energy leading to that intermediate. The activation energy for the ortho is slightly more than that for the para. And we said that is because para is preferred due to resonance preferred, okay? And that's due to less steric hindrance. The nitro group here is free, but the ortho group here, you see, it's close to the original substituent. So therefore, this is preferred over ortho. And meta is the least, because look at how high the hill is. And so that has the highest activation energy, and you get the least amount of the meta product. Okay, so this is the same picture as the previous one. More ortho is formed. Why? This is because of the statistical distribution. Okay, statistical distribution. What does that mean? You have more, well, you have two ortho and only one para. See that? So more ortho is formed because there are two ortho positions and only one para position. Okay, so the likelihood is you should get, theoretically, you should get 66% of the ortho and 33 or 34% of the para. But then also remember, the CH3 group is a small alkyl group. All right. Okay. Now we're going to look at something new. So we are going to talk about other types of activating groups. The alkyl group, that's, if you remember from the list, that's the least activating. Then you have the methoxy group or the OH group. Those are more activating. So the methoxy group, compared to benzene, okay, not compared to something else, compared to benzene. So if you have an ether like this is the methoxy group attached to the benzene ring versus pre-benzene. Then the methoxy group, or the anisole compound, reacts 400 times faster than benzene. The methoxy group delivers electron density via resonance. Okay, so how does the methoxy group activate the ring? Activates the ring through resonance. All right. So the oxygen of the methoxy group has lone pairs, and you see how they've drawn the first resonance structure. Oxygen takes up the positive charge and gives its electron pair to the ring. And then we can draw more resonance structures. You have to practice drawing resonance structures because this chapter involves drawing resonance structures. Okay. And then you can draw one more. You have to remember these patterns. Let's see what happens here. Let's go to sit on top of this. All right. And then if you draw the last one, you'll get the product that you started off with. So what happens in this case? The electron density of the benzene ring is increased. You have a negative charge here in the ring, negative charge here, and negative charge there. You see that? So the electron density of the ring is enhanced. See that? And where do you see these negative charges? That's something interesting. You see the charges at the, what position is that? What position is that? What position is that? You see the electron density greater at the ortho and para positions. The negative charges are at the 2 ortho and 1 para position. See that? So when you have an electrophile come in, the electrophile will prefer, okay, when you have an E plus coming in, it'll want to go to the ortho position, or it'll want to go to the para position, or it'll want to go to the other ortho position. You see that? So I can tell that the methoxy group is ortho-para directing. Now sometimes the methoxy group, if it's not controlled, it activates the ring so strongly. So normally, if I want to add a bromine group, okay, if I want to bring an a B plus electrophile, so I will use Br2 and FeBr3. And I would expect this to happen. BR is a small group, so I'm going to say you're going to have more of the ortho product. Okay, major and minor. This is what I would expect. But this is very strongly activating. And in some cases, see, no catalyst is needed. No catalyst here. And he goes crazy. He adds more BR groups than expected. Okay, so this is expected. And this is what is obtained. So it has to be controlled a bit. Okay, so even without a catalyst, poly substitution occurs. Okay, and so sometimes we'd have to find other ways to control this reaction. And they even get 100% of this. It's like boom, you get 2, 4, 6 tribromo anisole. But activators in general are what? Ortho, para, directing. So that's an exception. Now, with bromination, that could be an exception where the reaction takes place very fast. But if you have a reaction like nitration, what is it that we see? The nitro group, remember the Lewis structure for the nitro group, positive here. Okay, it's not just one atom like the Br. You have 3 atoms in the nitro group. And so because of steric reasons, you get less of the ortho and more of the para. You see that the yield is reversed. You get about 66% of the para and about 33% of the ortho, and still very little of the meta. Okay. So activating groups are generally ortho, para, directing. Now we're going to see how resonance actually stabilizes the ortho product, the para product, and the meta product. Okay, just like how we did with the CH3. So I'm going to show you OCH3, and you have the nitro group coming in. Okay, this is the nitro group that's coming in. It's not attached to the ring yet. So now open this up. All right. Now let's see what happens. So the process starts. You have a positive charge that's adjacent to the oxygen. And then they're going around and drawing the resonance structures. See the positive charges next here and there. And how do you get this extra resonance structure? I'm going to look at it as coming from here. Okay, I'm going to say this is D to show, and this is the change that happens to show how this is converted to that. See? So let me draw it separately so you can see it better. I don't think they did a good job there. Or at least I think so. Okay, I'm going to take the first structure and I'm going to show how the fourth structure is derived. Okay. We have the positive charge there. You see that? Now, this is 1. To go from 1 to 4, that happens. So what does the oxygen do? The oxygen now has a lone pair, and the positive charge is adjacent, on the carbon is adjacent to the oxygen with 2 lone pairs. So then the lone pair moves over, and you have a double bond here. And so you can show it going directly from 1 to 4, or like they have shown it here, you can also show it going from 3 to 4. But all in all, you have a fourth structure, and that's possible only because your positive charge is adjacent to the oxygen with the lone pair. Or if you have nitrogen with a lone pair, the same thing will happen. So you have extra stabilization because the positive charge for 1 happens to be there, and that atom outside the ring happens to have a lone pair of electrons to donate. So you have an extra resonance structure. Now let's see what happens when the anisole tries to grab a nitro group Okay, so it should go there. So this guy, it attacks this position. The positive charge is created there. Now, like with any other meta attacks, you see this positive charge evades being at that position. Okay, the positive charge is never there when you have a meta attack. So then that extra structure is not possible. And again, when you have the para attack, so this is going to be more like the ortho case. Positive here, and it should attack here, right? look in the textbook too. You'll see how it's drawn in case this looks messy for you. And you'll see the positive charges here. You can see this is the crucial one. And then here. So you can draw 4 from 2. Okay. Same as what we did with the ortho attack. And you have an extra structure. So what's the conclusion? Resonance stabilizes sigma complex. So these resonance structures, okay, they are called as sigma complexes of the ortho and para attacks. In other words, OCH3 is an ortho-para director. Okay, it's an ortho-para director. Got that? Okay. Now let's look at some energy diagrams. This is slide 45. Again, depending on the incoming substituent, your ortho's activation energy may be higher, much higher than that of the para. So para is the major product. And this is formed in very small quantities, okay? So this is the least favored. Still, you'll get a lot more of the ortho than the meta. Now, we are going to look at deactivating groups. Example of a deactivating group is the nitro group. So how does it play a role as a deactivating group? It is both inductively deactivating. You look at the group, the atom that's attached directly to the ring, that has a positive charge. Now you look at CH3, which is a weakly activating group. Okay, this is activating, and this, because it's attached to hydrogen, this will have a delta minus, and so it pumps in electrons into the ring. What does the nitro group do? It takes electrons away from the benzene ring. You see the difference? This is an electron withdrawing group, and this is an electron donating group. And how does it perform as an electron withdrawing group? It's through inductive effect. And this is also through inductive effect. Now, another way in which it deactivates the ring is withdraws electron density through resonance. So inductive effect also depletes electron density from the benzene ring, and then also through resonance. So that's why it's a strong deactivating group. So you have the nitro group. Look at how the Lewis structure is drawn. You should be able to draw all of that. And then this goes over and moves there. And then you get a positive charge, and you can move that. And look what happens here. This moves, and then you have a negative on the second electron as well. And if you're drawing resonance structures, yes, you have to show all the correct Lewis charge for the whole molecule or ion. Okay, now I'm going to draw one more. Okay. It's a lighter pen. Okay, it's a bad resonance structure. Look at all the charges. Okay, it's not very stable in the first place. So now, how does it withdraw electron density? Look at what the ring has been given by the nitro group. The ring has positive charges at the ortho, para, and other ortho position. I'm going to compare this with what we had in the case of the methoxy group. Let me pull that up. Okay, so nitro group introduces a positive charge into the ring. All right, that's why we say it withdraws electron density from the ring, or it deactivates the ring. See that? Nitro group introduces a positive charge, and therefore we say it withdraws electron density from the ring or deactivates the ring. Let's see how this is different from when we had the OH3 group. What did the OH3 group give the ring? It gives negative charges at the two ortho positions and para position. So this guy clearly activates the ring. Nitro group takes stuff away from the ring. Okay, so that's how the two are very different. And where does he take the electron density away from? And that's from the two ortho positions and the para position. You see that? So an electrophile coming in would avoid, because the electrophile is already positively charged, he's going to avoid the ortho position, he's going to avoid this ortho position, he's going to avoid that para position, and where would he go? He will go to the meta position. That's why deactivating groups are meta directors. Okay, now we'll see the result of all of these things. Like I said, the ortho positions are not electron rich. Only the two meta positions are electron rich compared to the other positions. And therefore, look at this. You get 93% of the meta 6% of the ortho. This is because you have two positions, okay? Even though you get 93%, if you compare nitrobenzene with pure benzene, this guy is very, very slow, okay? So you should be able to compare their reactivity based on if the group that's already present is strongly activating, moderately activating, weakly activating, weakly deactivating, moderately deactivating, or strongly deactivating, okay? So you have to know that list. Now, when you have nitrobenzene and you're trying to introduce another nitro group into the ring, and that's possible. Now, let's see what happens when the nitro group goes to the ortho position. So it goes there. When it does that, see there's a positive charge here. And you draw the other resonance structures like before. There's a positive charge here. There's a positive charge there. In other cases, the placement of a positive charge at that position was helpful. Okay. What about here? These two positive charges are going to repel each other. Let me draw a better structure for the first one. Let me see if I have enough room. So you have a positive charge here. And then open up this nitro group. Okay. So these two positive charges are going to repel each other. So this structure is not a stable resonance structure. Okay. So this has only two good resonance structures. See that? So when you have, and this is not so just for a nitro group being in the position, because see, this guy is not affected at all. It could be a Br, it could be a Cl, it could be another CH3. But when you have the first substituent as your nitro group, this resonance structure is going to be very unstable. Now I'm going to do the same with the ortho attack. I'm going to show you how that's very similar. This produces a positive charge here, positive charge there, then positive charge there. Same thing happens, the nitrogen has a positive charge, and so the two charges repel each other. So this is an unstable resonance structure. I'm going to draw the same here. This is unstable. So then this leaves you with two good resonance structures. Now what happens at the meta position? Okay. Now you have a positive charge here, here, and there. Now this spot is avoided. So all in all, you have three good resonance structures. Three good resonance structures. So which one do you think will be preferred? This will prefer sending in any electrophile to the meta position. And we have a demonstration using the energy diagram for the ortho. Could be due to steric hindrance. The ortho and the para positions are not preferred on the meta attack. Compared to these two, this is lower. See that? Compared to the other two, this is lower. So the electron withdrawing group deactivates the sigma complex from ortho and para attack. So it prevents it from going to the ortho or the para position and sends it to the meta position. See that? Okay. Now, what about halogens? If you look at the Cl, the Br, the I usually, these are weakly deactivating. This is an exception. Usually deactivators are they are meta-directing. Electron donating groups are ortho-para directors. Electron withdrawing groups are meta-directors, except for halogens. Halogens are weakly deactivating groups that are OP directing. Okay, so they're first of all weakly deactivating. Why are they weakly deactivating? Because halogens have high electronegativity values. Therefore, they are electron withdrawing. So if you have a carbon attached to a fluorine, this is delta minus and this is delta plus. He has an EN value of 4 and this is an EN value of only 2.5. You see that? So halogens withdraw electrons by induction, makes it deactivating. But another reason, halogens also have lone pairs. So you remember with the methoxy group that oxygen had a lone pair, but it had two lone pairs, and he was able to give one into the ring. So halogens donate electrons through resonance, and therefore they are ortho-para directing. Two things to keep in mind. They are weakly deactivating and they are orthopara directing. You have to remember that. And you know why. Okay. So if it is a deactivator, usually it'll send it to the meta positions. But halogens are OP directors. Again, more explanation. Why is it deactivating? Cl or F or Br. This is 3.0. This is 2.5 in terms of En. See how it can withdraw electrons? But then the Cl, the same Cl, has lone pairs. In fact, each of them have 3 lone pairs each. So they are electron rich. Okay. E rich. Can send electrons into the ring. So I'm going to draw some more. And you'll see that it packs up the ring with negative charges. Okay, there's a negative charge here. There's a negative charge there. And I'm going to have one more. And the Cl plus carries the positive charge. So Cl plus says, okay, I'm going to give you the electrons, okay, give you life, and I'm going to take the positive charge on myself. Okay, so this in fact reminds me of what Jesus did on the cross for us. So he takes up the positive charge, the sin of the world, on himself, and he gives us richness. So that makes us electron rich. I like to use this analogy, but you can only use that with students who know organic chemistry, right? Nevertheless, I always talk about it when I do this section. Okay. So this is an electron-rich ring. And of course, you can draw the last one, and it'll give you the original structure. I'll let you finish that. So the halogen X group makes the ring electron rich. Okay. And then at what positions does he make it electron rich? The ortho and para positions carry the negative charge. Okay, the ortho and para positions carry the negative charge, but they are deactivating. We need to classify them as deactivating because of their electron withdrawing power. Okay. Now this is the same as with the methoxy group. I'm going to let you all draw these to start it off. Let's look at the resonance structures. So you have the plus here, and from the plus, you can go from resonance 1 to resonance 2, resonance 4. And you will see how that positive charge is stabilized. I'm going to draw one. Cl, all its lovely electrons. and you can go directly to 4. Okay, you can do 1, 2, 3, and then from 1 you can go to 4. Remember to review drawing resonance structures, look at patterns. Okay, so what does CL do? CL says, okay, I will take the positive charge over. See that? And so this is similar to the OH3 group in the ring. Okay, you had a good chance at looking at this. This is structure 4. Okay, so just like those activating groups that had an atom with at least one lone pair, you can show the extra stabilization. It's the same way with the halogen. So you have an extra structure. And with the meta, look where the positive charges are. No extra resonance structure. And similarly, when you have the electrophile attack the para position, you'll have an extra structure. It's because the positive charge is adjacent. Okay, so here you'll go from 2 to 4. So now it makes sense as to why the halogen is an orthopara directing group. Okay, so you should be able to explain why something is an orthopara director using resonance structures. Okay.